Hey everyone, my name is Koushik Krishnan. I'm a site reliability engineer at Yugabyte. Yugabyte is a distributed Postgres database, open source distributed Postgres database. And today I'm going to be talking about runbook automation with Jupyrest. So when we talk about runbooks, they're a very important tool for any site reliability engineer. A runbook is a well-defined set of steps to address a particular situation or incident. And not all runbooks are created equal. So runbook quality can have a big impact on time to mitigate, or TTM. So while a good runbook has unambiguous and actionable steps, the best runbook is the one that has the fewest unambiguous and actionable steps. And that's what we're striving to do. So when we talk about the steps in a runbook, there are really two main categories. There's investigation steps and mitigation steps. An investigation step is a step that answers a question like, what happened and why did it happen? And a mitigation step is a step that answers the question, how can I fix it? Now, as an on-call, your priority is to mitigate an incident, not to do a full root cause analysis. That's better left for the postmortem. So ideally, your runbook should really focus on only doing mitigation steps. However, in order to know what mitigation steps to take, you'll have to do some amount of investigation before that. And investigation, these steps are generally time consuming. They induce a lot of cognitive load on the on-call. But unlike mitigation steps which will make a change to the state of running system, like rolling back a deployment or updating a configuration, investigation steps are read-only. They're just diagnosis. So they're actually very well suited for automation. So we can talk about how to actually automate these complicated investigations. So automation is a good way to do this. When we talk about runbook automation, there are many tools out there to do this. Many incident management platforms and observability platforms will have some kind of an automation component. And these are usually proprietary places where either like low code or no code, where you can encode your logic there. But another tool that's recently been used a lot for this same purpose is the Jupyter Notebook. So a traditional runbook will contain some text and some code snippets, and you will have to read it and kind of parse through it yourself. A Jupyter Notebook will also contain some text like Markdown, as well as some code. But unlike a normal just written document, you can actually execute a Jupyter Notebook. You can treat it like code, but when you consume it and read it, it can be read like a normal document. So whoever's reading the runbook doesn't need to know the language, or doesn't have to be like an expert in the actual the code blocks themselves, but you can add a lot of interactive media like graphs, charts, tables, and widgets in the Jupyter Notebook. And that's just thanks to the prevalence of the ecosystem and all the plugins that are out there. So I'll give a brief intro into Jupyrest, which is a Python library I wrote to help solve this runbook automation problem. I won't go into all the technical details, but I'll just give you a high-level overview of what it does. So the Jupyrest is a Python library, and it's a tool that can let a client execute a Jupyter Notebook with parameters using an HTTP post request. So what this means is that you can take a notebook and turn it into a REST API with a well-defined input schema. And what I like to say is this is like notebooks as functions. Under the hood, Jupyrest is a very thin layer over the popular Papermill library, if you're familiar with that. So I'll just show you how Jupyrest works. So imagine I have a notebook like this. This one's a low disk space run book. At the top, there's it takes some parameters, and then at the end, it's going to ask me to run a particular shell command using those parameters at the top. This is a very simple run book, but this is just an example. So if I wanted to turn this into a REST API so that someone can execute this notebook with parameters, what I'll do is I'll basically, I'll have this other file alongside the notebook that details the input schema for that notebook. So you can see on the left here that I'm using a JSON schema. I'm representing the schema using the JSON schema spec, which is used by OpenAPI and Swagger. And here it's saying that I need customer ID and IP address, and they're both required properties. So these two files will tell Jupyrest that, okay, like if someone's going to execute this notebook, this is the input schema that's necessary for that. And a client can, and when you start the Jupyrest web server, a client can execute the notebook using a post request like the one shown below. When you make that post request, what happens is we'll insert a cell. This is a lot of this is using the Papermill library, but we'll insert a new code cell into the Jupyter notebook that contains the parameters from that HTTP request, and then we'll execute that the notebook from top to bottom. And when this execute notebook, when you see it, you can see that at the bottom I have my pre-computed mitigation steps. So you can imagine that all that prior to that, I have automated a whole bunch of investigation. At the end, I can just have tell the on-call, like, hey, you need to do these 3 or 4 steps to mitigate this incident. So in practice, the way this works is you have some kind of alerting framework that creates an incident, and most incident management platforms have some kind of a webhook feature where you can attach a webhook for any time an incident is created. And so that webhook could be a call to your Jupyrest web server, wherever it's running. And that will let you execute a particular notebook with parameters from the incident. So things like the incident ID, the incident time, Kubernetes cluster name or namespace, et cetera, region, whatever it may be. And you can pass that into the notebook. And then Jupyrest will parameterize the notebook. It'll validate against the schema, execute the notebook, and then the response is just that executed notebook, which can be attached to that incident. And when I had implemented a version of this at Microsoft, and the cool thing was that when someone got paged, by the time they actually got to their computer and opened up the incident, the notebook was already executed and available to them in the incident. So they could just open it up. It's like HTML file. They can just open it up, and all the investigation would have been done. And all they need to do is just follow whatever mitigation steps were at the bottom, which is a great way to save on, to improve a TTM. So this is good. It's a nice way to automate a whole bunch of things, but I think there's really a lot of opportunity to go much further than this. And the question is really, how can I get the most out of a Jupyter runbook? Because if you imagine you have so many different types of incidents, and an equal or greater number of runbooks, how do I write these runbooks in a way that is structured, scalable, and modular? So we're going to consider an example service here so I can show you how you can do that using the Jupyrest Python library. So example service here, I'm going to have a service where you have a customer that has an HTTP service. An HTTP service will have it replicated across 1 or more different replicas for fault tolerance and high availability. And each replica is then hosted on a virtual machine. Now, this is a sample service architecture, but you could imagine something like Kubernetes pods and namespaces and whatever it may be, however your service looks. So interesting, I don't see that slide. Okay, so we have our, the first thing we're gonna do is we wanna design our alerts. So we're gonna have 3 different alerts, one at each one at different layers of our service stack here. So at the lowest level, we have our a slow disk alert, basically a low, like anytime there's a high disk IO latency, we'll have an alert there. We'll have another alert at the replica or application level when we find high replica resends, or basically when there's high replication latency between replicas. And then at the top layer, we'll have a alert for SLA violation. We'll have to, we'll provide every customer with an SLA agreement. And whenever we are at risk of violating that SLA, we want to be alerted in that case if they're seeing an increased number of errors. So the question now is, okay, what severities do I attach to these different alerts? And you can argue, well, all of these are important. We should be woken up for every one of these things. But the reality is that in a public cloud environment, the slow disk and high replica resends, things like network latency, those things will happen and there'll be blips, and it's not always useful to have to investigate those every single time they happen. And if your service is designed well, usually these things won't actually impact the customer. That SLA violation alert, however, this is a alert that is less noisy in that it's much more indicative of a customer experience. So a degradation in any of our service level indicators on which our SLA is written, then that would indicate a degraded customer experience, which means someone should look at it as soon as possible. So we're just going to say for now that SLA violation alert, that's our high severity alert, and our low severity ones, which means no one's going to be woken up for these, are high replica resends and slow disk alerts, mostly infrastructure level alerting. So, okay, we have this. So now how do we go about, writing and authoring these investigations? So the first thing we're going to do is we're going to model our service domain in code. So this is a concept taken out of domain-driven design. If you're familiar with that, we're just going to create, these concrete entity objects that represent components in our service. So this is what that looks like. As you can see, Jupyrest has some base classes that help you write these entity objects. But these are the 4 different components I laid out before: node, replica, service, and customer. Pretty straightforward. One thing to note here is that every one of these entity objects needs a unique identifier, which is it just as the domain-driven design pattern says. And another thing is that each class has a namespace that designates the type. So now that we have these 4 our domain objects laid out, the next things we're going to want to do is to model our alerts in a similar way. We can use a domain-driven approach to do this as well. So we have 3 alerts we talked about, so we can represent them with these 3 Python classes: replica resends, slow disk, and SLA dip. Now, the information about these is very basic, but you can imagine you can add all kinds of things like different numeric values or extra log data or whatever it may be. But for here, I'm just keeping it very simple. So here, okay, we have all our Python classes. How does this look in practice? Consider this incident timeline. Like I said, we have these low severity alerts. So these will generally fire a lot more frequently than our high severity incidents. So in this case, we're going to have like 4 low severity incidents, and then we'll have a high severity incident. Now, what we want is we want to be able to leverage the investigations made, the automated investigations made in those low severity incidents to help us investigate the high severity incident. We want to use the noise to our advantage. So what that means is that every time a Jupyter notebook runs for one of those low severity incidents, that notebook should be able to save its whatever it investigated, save that in some form, so that when we investigate the high severity incident, we can reuse those findings. We don't have to keep going back to our log store to keep running the same queries over and over again, which will take more time. So well, let's see how this works. So our first instance that we're going to get is a slow disk detected on node 212. And I have here the slow disk runbook that I've written to that would be executed for these types of incidents. Because I'm using Jupyrest, the input schema would look like this. I'm expecting a node ID, incident time, and incident ID from the actual incident. And then the client, when they want to execute this notebook, would make a call like this. So this is what the webhook this is the request the webhook would make. So this notebook in particular is not very complicated. All it's doing is creating this node object and then the slow disk object, and saying, hey, this node has a slow disk. And then you see that last line there is calling save graph. So what I want to note is what this is doing is it's converting those domain objects, the node and the slow disk, into a graph-like representation. Jupyrest knows how to convert these Python objects into a graph. So how does that look like? It will generate a file that looks like this. This is called, this format is called the turtle file, TTL. And if you're familiar with the RDF triple store, that's essentially what this is. It's a implementation of a graph using a triple store. And obviously this is not very useful to look at. So if we visualize this with GraphViz, we can see this is what the graph looks like. So we have our slow disk incident represented as a vertex. Then we have the edge, which is a node, and then we have our node 212, which is another vertex, which is saying this node has a slow disk. And then we can save this file in some cloud storage. Okay, so our next low severity incident is replica resends from this one replica to another. This is the replica resends runbook. It's doing something very similar to the slow disk runbook. Here it's just creating the objects and storing them as a graph. So we have our two replicas, source replica, destination replica, and then we construct the replication resends object, and then we save this object as a graph. And what that looks like is like this. We have a replica resends object, and then we have an edge for source replica, an edge for destination replica. And one thing to note is that when you're designing your domain objects using Jupyrest, you don't have to really worry about edges or vertices or anything like that. That's all taken care for you by the library. You can use the same principles from domain-driven design, and these things will get saved for you as a graph transparently. So the next incident here, incident 3, you have a slow disk on node 900. Again, this is what that would look like, slow disk. We have an edge for a node and then node 900 there. And then 4, another replica resends incident from this replica ID to that one. And then it saves this little graph here. And nobody's really been woken up at all during this whole time. These are just all happening in the background automatically with these low severity incidents. So now we come to our high severity incident. This is a SLA dip incident for our customer Patty's Pub. This is our top customer, and we have very stringent SLAs for this customer. So the runbook that we have associated with this high severity incident looks like this. And mostly it looks the same. We're creating a customer object and then the SLA dip object. But the one thing I want to point out that's different is this box here. What we're doing is we're getting the last past incident IDs, be it like the last 1 hour or last 2 hours. We're getting all the previous incidents. We're reading the graphs generated by all those previous incidents, and we're concatenating them all to create like a high level picture of like, okay, what happened here? What happened in the last 30 minutes with this customer and all of its associated resources? So when we call like visualize, we're going to get something like this, which is very hard to read, but I have it open here. And so when you look at here, it's very similar to what we've been seeing. We have this incident SLA dip. It says the SLA dips for this customer, Patty's Pub. And then this customer, like I said, has services. You can see the edges there. And then, so we have our service topology represented here, where services have replicas, but we also have our incidents represented here. So this node 900, it belongs to this replica, but we also find that the incident for a slow disk is also represented in this graph. And that goes for every other kind of incident that we've saved previously. So this is another replica resends incident here. So we have like all of our information here, which is a nice way to see what's going on without having to scroll through a bunch of logs. And sometimes if this graph is small enough and simple enough, you might be able to find where the root cause is just by looking at it. But even this example, it's not trivial. And certainly for more complicated examples, it will definitely not be trivial. So how do we encode some root cause analysis logic on top of this graph? Well, like I said, because we're using a very well-known standard for the RDF triple store, we can run what's known as a Sparkle query on this graph that can encode logic that will do some like a heuristic as to find out what the root cause is. Now, if you don't know the Sparkle language, this might look fairly confusing. So what this query is essentially doing is saying, find me the nodes with slow disks that are causing replica resends for a customer experiencing an SLA dip. If that doesn't look at all like what this text says, trust me, it's actually a very intuitive language. But yeah, you can basically include these queries as part of your notebooks. And by the way, this is again, you can run this in a notebook with Python code. There's already a Python library to do this. So you don't need a running server anywhere or anything like that. You just need to grab these graph files and you can run these queries in the notebook. So the output of this root cause analysis logic says, okay, this node 212 is actually the culprit node. The node 212 is the one that has a slow disk. It's causing these replica resends, which is causing the SLA dip. And one thing that's interesting here is that we actually had two nodes that had slow disks, but only one of them is the root cause. So we eliminate the noise of having that other node 900, that had a slow disk, because we determined, yeah, it had a problem, but it didn't actually manifest. We can do like a traversal up the graph and find that it didn't actually cause any problems up the stack. It was a very transient issue. So no need to perform any mitigation actions there. This would be something that's very hard to determine just by looking through your log data, because you might see these two nodes and determine, hey, both of these have to be the culprit. So with this, now you've got your full like end-to-end scenario where you can leverage your low severity incidents, all the little, partial graphs of those little investigations, and to give you a much better high level picture during your high severity incident investigation. And this will also, and because you have all these notebook executions, you now have a much better way to present a postmortem or understand what actually happened during this incident timeline. You don't ever really need to go back to your log system. You can just look at these graphs, and it's a much more contextual. And we generally like to think of systems like these as a graph. So representing them like a graph and diagnosing them as a graph, it's very natural. So some takeaways here. So with this library Jupyrest and the Jupyter Notebook ecosystem, we get a structured method for performing automated investigations. This lets us write really actionable runbooks that don't require a lot of time-consuming investigations, but we can still encode complex investigations in them. We also are able to leverage our noisy incidents to aid with our high severity incidents only when we need them to. So we can have more lower severity incidents and then fewer higher severity incidents, ones that actually indicate customer impact. And Jupyrest, like I showed, it has the ability, you can utilize this automation for like graph-based root cause analysis, and encode that right into the runbook without having to describe it in a much more verbose manner in a traditional written runbook. And lastly, Jupyrest, it lets you take ownership of your runbooks. You don't have to put them in a proprietary platform or use the special tool. Jupyter notebooks can be run on your laptop. They can run in the cloud or your own data center. And there's so many different plugins for talking to all kinds of different data stores already out there. So you just get all of that for free. And then Jupyrest just kind of lets you make use of that in an SRE context.